we will have our next speaker, Dr. Madison Lasich from Mangosuthu University of Technology. She is a senior lecturer there of chemical engineering, and she will talk to us about HPC and chemical engineering thermodynamics at MUT. Over to you, Madison.
Hi, thanks, Tubani. Okay, so I'm going to be kind of doing like an overview of all the basically how we've used the CHPC's resources. That's what Werner asked me to talk about because we've been using their facilities for quite some time. So just for those of you who are not too familiar with Mangosuthu University of Technology, it's not a big university. There's a little picture of campus. There's the main entrance there. What's not pictured here is there are some new buildings at the back there. And this is like sort of the quad, and my office is about there, overlooking the quad. So it's a previously disadvantaged University of Technology in Umlazi, just south of Durban. About 10,000 students, more or less evenly split between the three faculties, so engineering, natural science, and management. I think there is a guy in chemistry who also uses the CHPC's facilities in Kululego, really nice guy. We don't really have many postgraduate programs. In engineering that we have, the best you get is like BTech/advanced diploma. For those who don't know, there's been a sort of a changeover in engineering qualification. So what was the BTech is now called the advanced diploma, but it's the same thing. So my research group, the Thermodynamics Materials Separations Research Group, it was started by me and a very old, we go way back, Prof. Kaniki. We were both at UKZN doing our postgrad. He started at MUT quite some time before me, and when I joined in 2017, we started working together. So he does experimental stuff. He gets around. He's got a lot of collaborators everywhere, as you'll see just now. We've got one postdoc. She's at the back there, Victoria. We've got a couple of masters and doctoral candidates, and we've got some BTech/advanced diploma students. The BTech is, I think we're still phasing it out. There are some students who are still in the pipeline. They get like small semester-long research projects to do. So they don't do a heck of a lot. And it's a bit of work when supervising, because we basically have to, the ones that I supervise anyway, I then train them how to use like Material Studio, whatever. And it's like literally just for a semester. So, and then it's every semester, like every year. So, now I'll just add that as a note, before using the CHPC, I'd been using a very, very, very old cluster called Ruby in Borås in Sweden, which I had access to via my then supervisor at UKZN. It was like cannibalized from was an old Beowulf cluster, cannibalized from bits and pieces. I don't know how they kept the thing running. And it was not very fast at all. One incident I can remember was, I think it was at the one European Symposium on Applied Thermos. I knew there one postdoc at the time, and he was doing like some polymer nanocomposite simulations. And from the time when he submitted his abstract to when he had to do his talk, the simulations hadn't reached equilibrium yet. So what his results were was he presented extrapolations of what he thinks the results might be. Okay, so some of our collaborators, just like a long list there. I've highlighted the ones that I'm involved in. Kimberly-Clark I add simply because I've been collaborating with someone there, but we haven't used any corporate resources, and terms and conditions apply. The views of the author do not represent the views of Kimberly-Clark Corporation. The Nexa project, which I'll talk about, I was only told yesterday by my PhD student who worked on it that we can now actually go and publish more stuff from it. So he's going to go to a conference in Florida. So we did publish some of the work, but not very much because of non-disclosure agreements. Okay, so the research areas we have, we basically, all of these research areas have experimental element, but then all of them do have an element of using the CHPC's resources. So we've got the list there. So we're the thermodynamics research group in a sense. So we do like solid fluid interactions, kind of like physical chemistry stuff, phase equilibria, and then we do a little bit of process design. So taking these first two results and then coming up with something a bit more practical, like at least at the unit ops level. Prof. Kaniki's done kind of much more practical stuff in that sense, especially in natural products. I've done a little bit in gas separations. Okay, so just to show how important the CHPC is to what we do, they save us a lot of time and money. We know university procurement's not very fast, so we can get like screening and some like nice predictive stuff done. and also we're not a big institution and we don't have a lot of manpower. So it's like very helpful for kind of like getting lots of work done with few resources, especially in human capital. And the nice thing is for the simulations, you can control whatever you want, make generalizations, which I'll talk a little bit just now. And we have used some of our computations to sort of understand better or improve existing models out there that are used by other chemical engineers. Okay, so some of the work that we've been using. So this, I haven't really used COMSOL multiphysics myself. That's been my PhD student, because he did some CFD for his work. His work was like an experimental CFD and molecular dynamics. Then I've used extensively TAUE quite a bit, even before. I don't know if anyone's familiar with TAUE. Paula probably is. And then materials you'd have used a lot. Okay, so this is just a summary of like most of the projects we worked on, especially ones that involve the CHPC, so clathrate hydrates. Trying to find, like basically the cement one was I was just playing around with it because why not? And then we found some interesting results. Looking for applications for bentonite. This is the Nexa project over here. This is a collaboration with DUT, which was a very strange project to work on. And this is the newest one that I've started working on with some other people from DUT and also colleagues within the institution. The biggest research group in my department in chemical engineering at Mangosuthu is the water. It's like water pollution and environmental remediation. I can't remember the full name of the research group, but Prof. Bakare's got like a really nice kitted out lab for that. They do all experimental stuff, and we started now trying to add some computational value to his work. So your clathrate hydrate stability projects. So I'd done this during my PhD, and now what I've done since then, since joining MUT, is to try and look at some of the models we developed. So during my PhD, I developed a protocol to predict your thermodynamic stability from grand canonical Monte Carlo simulations. So those kind of mimic your stochastic simulations that mimic your adsorption processes. You get your adsorption isotherms, then you plug those into a statistical mechanical model that's widely used in gas hydrates, and you can get the phase equilibrium without touching the lab. However, not very good because of the force fields and some simplification along the way. So what I did was to fiddle around with how can we tweak this model to make it work. One of the things we did was to play around with the unlike dispersive interaction term. Size term didn't make a difference, but the energy term did. And we noticed that a nice handy assumption you could make was to assume for structure 1 hydrates, which are the common ones like methane, that the cavities are more or less the same. They have a similar approximate volume, but they have the one is like oblong and the one is more round, but the volume is more or less the same. So you've got some applications over there. So here's the sort of the protocol that we developed. So you basically go from this, your adsorption isotherm, to this. This is a bunch of different models with different fitted parameters. And here's your experimental results. So we can see we can get pretty close to experimental results, actually. So yeah, that's basically it for the gas hydrates. We haven't worked on this one for quite a while. Although I'm looking at getting back into it, but probably we won't be using the CHPC's resources for that because I'm looking more at something less computationally intensive. This middle step here, strictly speaking, like chemical engineers like stuff that they know. So you'll see there's a lot of fitting to the standard adsorption isotherm models. Personally, I'm not 100% sure that it's really necessary all the time, but the chemical engineers like what they know, so we include it. Okay, now cement, I'd literally just started playing around with it because I stumbled upon, it's from 2009. It's the first accurate molecular model of cement hydrate, despite the fact that it's been around for thousands of years. So I thought, like, let's play around with it. So we basically did adsorption of like like what you might get from natural gas or biogas. So like H2S, methane, ethane, ethene, whatever, all of those things. And what we kind of got some interesting results. We found that the cement hydrate could select between ethene and ethine, funnily enough, and that it absorbs your sour gases really, really well, which also explains corrosion in cement. So we were then kind of trying to look at, could you use like waste products, like cement waste, because it has lots of embedded carbon in it anyway, just to see what would happen. And then we also looked at, this is with someone from Kimberly-Clark. Let's look at cellulose concretes. Can we sort of tweak the cement hydrates the cement cellulose ratio to improve corrosion resistance. The results there are not really, but that's a result, I guess. Okay, so this is what your cement hydrate looks like. It looks like a mess. Basically a bunch of silica chains. What we find with the H2S, why it's so problematic, I guess, from a corrosion point of view, is that there's just adsorption sites everywhere. And the structure, you can't just look at it. It's not like a zeolite, which are nice and they have a nice geometry about them. Cement hydrate doesn't have that. So yeah, it's a problem. Okay, the bentonite stuff, we looked at a few different things. First, we started looking at making like polymer bentonite composites with humid air. Didn't really go very well. That was a project with UKZN. We've had some mixed results there. What we did look at though quite extensively, especially going forward, is to do process design, especially using bentonite, because it's like it's a widely available clay mineral. And we looked at using it for gas separation and also for improving renewable like producer gases and biogas. So we kind of got some interesting results there. And this is where we have the process design element. So basically what we do is we start off with grand canonical Monte Carlo simulations done using the CHPC's facilities. Then this step is, I feel, superfluous in this workflow. But like I said, the chemical engineers like what they know, so we include it for that sake. And then we go to this step here. This is just done on a local PC. I've written a little routine to basically model a pressure swing adsorption units at the operations level. So we, in principle, we could just skip this and go from there to there, but we include this anyway for other people. And we can then get, that doesn't give you the super realistic performance, but it gives you like best case scenario. What can you expect at most? Because we don't include breakthrough curves, whatever. So it's just like equilibrium. So this ends up being this iterative problem to solve with like loading, regenerating, and then it converges, and then you get the bed performance, and you can stage multiple beds in sequence, whatever you want. We managed to get a little bit of an improvement in the calorific value of wood gas using bentonite in a PSA system. Not ideal, but this is a work in progress. It's not like a major improvement, but why not? We can try and make it better. Okay, this is this Nexa project. To be honest, I couldn't remember what we could report in and couldn't. I just included what I think is, like this is in the journal article that we got out. So this is some of the CFD modeling. So what we basically did here was CFD to look at fluorine gas flow in the reactor. We also did MD to look at diffusion into the surface of plastic. It's basically surface fluorination of polymers to improve their barrier properties. So now this moratorium is passed, so you'll probably see some more work coming from this project. It's the first non-disclosure agreement project I have to work on, which was kind of, well, interesting in a way. And there's my PhD student in Madison, who now has this little startup company with a couple of colleagues that do like engineering consulting work. This was the weird project. So this is with, I'm not going to try and pronounce his surname. His name's Kostya. He's from Ukraine. He's based at DUT. We kind of met by chance. And then I started looking at his work. He's worked in so many areas of physics. He's done like, he's like the physicist. But he's like a bit of a, he doesn't really work with other people. I don't know. I don't find him that hard to work with. Anyway, so we looked at, he developed this pair potential for superfluid helium, which I thought looked kind of interesting. Superficially, it resembles the Leonard-Jones potential, but with a finite repulsion term. So I guess in principle, with the right conditions, you could get lots of overlap between particles. So what we did is, so he's used it then to look at magma actually and got some quite promising results, because superfluid helium, Kostya will know the physics more. Superfluid helium, magma, and a couple other fluids, they're called Korteweg fluids, and they got like significant capillarity. But just out of curiosity, what we did is we thought, what if we do atomistic, like VLE simulations, MD simulations with that potential, what would happen? So this is your phase equilibrium, and that is this is just the diffusion coefficient. So over here, we kind of get, this is like a normalized density, normalized temperature, and then we looked at varying the size terms. This is a normalized size term. There's your critical point between like a sort of a vapor analog and a liquid analog. We weren't sure what to call them. It's not really like, it's not like a classical fluid. So this is kind of like your vapor, that's kind of like your liquid. And that's what kind of phase envelope you get. There's your critical locus of the critical points. And this over here is the diffusion coefficient. So like you'll see, these are a bit excessive, actually, as it turns out. These systems equilibrate quite quickly, but because we had no idea how this would behave, we just went a bit overboard. So this one actually converges within like less than 10 million Monte Carlo moves usually. And this usually converges within a nanosecond or less. So we just did 10 just to be sure we weren't missing something. So what we kind of identified is here's like a bit of a viscous fluid if you look at density, diffusion coefficient versus temperature trends. This over here is kind of like a rarefied gas, and this we're not sure how to explain that it's like it changes during the course of the temperature increase over there. What we did find interestingly with the RDS, which I'm not showing here, is that there are qualitative similarities to real magma, which we know that Sarkozy has shown that you can use this in magma from. He's not done this sort of simulations, but we're having these qualitative similarities. So it shows that this pay potential is kind of robust, that it's at least describing qualitatively things from very different systems, which is, it's a nice result, but we're not quite sure what to do with this at this point. It's more curiosity. Okay, this is a more recent project. We've been looking at, detecting pollutants and then from a remediation point of view. So can you select specific pollutants that are like from a common cocktail? Can you remove them from water bodies? So we're looking at polymers as well as carbonaceous materials. We've been focusing a lot on pharmaceuticals, and recently I've started a project with my postdoc on looking at like hormone contaminants that you get from agricultural runoff and so on. So this is the workflow that uses most of the CHPC's resources of everything. Apart from the Nexa project, because this uses their resources at every step of the way. So we do cell construction, then we do MD relaxation, then we do this step over here. So these are coupled together because we want to find the sort of like the minimum polymer chain length, because you can see that your cohesive energy density will converge. Why do a polymer chain that's 1,000 monomers long if you can get away with one that's 200 and the cohesive energy density is the same? There is some justification for that. And then lastly, we use these like the shortest polymer chains we can get away with to do some absorption studies. This work, we have published some of this already for some pharmaceuticals and fluorocompounds. The paper was rejected a couple of times. One of the rejections, the reviewer, said that basically they said they don't believe we did Monte Carlo simulations because Monte Carlo simulations of polymers are just a pipe dream. The computing resources don't exist. I don't even know how you can write that and then look at yourself in the mirror. Okay, so ongoing work. This is a project with Prof. Kaniki and myself. We're looking at biogas upgrading and cleaning. So not just using bentonite, but looking at other stuff as well. We're going to be we've started looking at this one I'm doing with my postdoc. We're looking at PLA in terms of water pollutant removal. And then this is an idea I have with a colleague. She's done water pollution research, especially with BTEX compounds, like your benzene, toluene, ethyl benzene, and xylene. And so what we have this idea to basically come up with so if you have the characterization of your carbonaceous solid, you can then get a good idea of its absorption profile for those compounds in water. So like a sort of a predictive way. So we do the simulations for a whole bunch of different pore sizes, different compounds, different compositions, and then kind of like fit that to experimental data, maybe make adjustments, and then you can come up with a nice, neat relationship between pore size distribution, the compounds concentration, and what sort of absorption you'd expect. That's the idea anyway. We'll see if it works. Maybe it doesn't, but at least we tried. Okay, so our acknowledgements, like I said, I'm not going to acknowledge Kimberly-Clark. We didn't use the resources, and the views of the author are not the views of Kimberly-Clark Corporation. But yeah, CHPC, I acknowledge DH here because I'm a fellow of the Future Professor Program. So, I mean, they don't provide really financial support, but we have to acknowledge them. NRF, because I got an NRF rating, and then our collaborators there's the research group. And then, of course, we have to acknowledge Nexa, who made all the experimental work possible for that project. It was done on site. An amusing tidbit from that project was the one paper that was published so far, one of the reviewers. So they did accept it with major revisions. And one reviewer said that they don't believe this work has any practical application, despite the fact that it's an actual reactor at Nexa. But anyway. Okay, thank you for your attention. If you want to get in touch with me, there's a couple of ways. Instagram is not for work-related stuff. Cool. Not at present, but it's been something I've been thinking about how I can connect that to what we've already done to expand on it, but I've not actually looked in it. Just new. Yeah. Hmm. Yeah. That will be interesting. It's just like,
200 picoseconds, and you only do one, get a proper error from it,
yeah,
and you can even put it in the realm that you can do quantum dynamics.
cool.
Various things. So
I'll check it out. It's just like,
but I'll chat to you more about that as well.
yeah, that'll be cool.
Hi, I was kind of interested by the fact that you were using molecular dynamics and CFD together, and I was just curious whether if you're allowed to tell me without killing me, which way it's actually which way it went, which way the coupling went. Was both? They coupled both ways? Were you using the CFD to give you like bulk properties or something that you could then?
They were not really, they're not really coupled. It was, so like my PhD student, as part of his work, developed kind of like so they were using the CFD to optimize placement of, because it's like surface fluorination of plastic. So the CFD was to optimize placement within the reactor. And then the MD was part of he developed a model that Nexa uses to basically model the surface fluorination reaction coverage, extent, etc.
Okay.
So they were kind of like complementary.
Okay, so they weren't coupled.
No.
Okay.
That was kind of necessary because it turns out there's probably proprietary information out there, but like all that's in the literature is just like recipes and no one really explained. I was just like, oh, we did this. We can't explain it. There's the result.